for the requirement of the electricity to operate the electrical devices, we need to generate electricity, and the generation is generally done in the power station or power plant, which are generally located far away from the locality or the utilization point. So that's why we need to carry the electricity or transmit the electricity from the generation point to the utilization point here. So a lot of distance is to be traveled by this electricity. So how to travel, how to transfer, or how to transmit? Through the electrical conductor. So those lines or conductors are called transmission lines, and that transmission of electrical power is conducted at very high voltages, say around 500 kilovolt. So this voltage is not the generation level of the voltage at the power plant. Generally 15 to 20 kV is the generation voltage. After that it is raised up to the 500 kilovolt and then transmitted, and then it is gradually reduced using the transformer. So for stepping up, the transformer is also used, and for stepping down, transformers are used. So transformers are electrical machines which are used to raise the voltage or reduce the voltage. So here you can see that transmission towers are there and transmission lines are there. So at very high voltage it is transmitted. Now these are the pictures where we can see generally in our society, say either in the pole there will be some transformers, pole mounted transformer, or sometimes in the switchyard also. Sometimes transformers are made with very small size for handling small amount of power. That's why these transformers are called low power transformer. And sometimes it is made with very large volume for handling a lot of power. So it is called power transformer. Now the transformer is developed with two major components, that is windings and the magnetic core. So windings are made up of metals, generally copper, though with other metals are also possible, but generally coppers are used because of its high conductivity. After that, magnetic material will be used, and that magnetic material may be ferrite or the iron sheets, and these iron sheets are generally used for reducing the eddy current. If we use one solid iron core, there will be a lot of eddy currents or localized current, and those localized currents will be generating some heat, so definitely some power will be lost, and that is called eddy current loss. Now the sheet steel, which are generally made up of silicon steel or cold rolled gate oriented material, that is CRGO, for better performance, better permeability, because magnetic flux are going to be conducted through that material. So definitely good magnetic material is preferable to develop the transformers. Symbolically, transformers can be represented by two windings or two solenoid or two coils separated by two parallel lines. The parallel lines are representing the separation between two coils electrically, and magnetically coupling phenomena is represented. So electromagnetic induction phenomena is represented by this structure. There will be two windings for single phase transformer, and the number of windings will be also differ to change the voltage level and current levels. So as the basic principle, as per the basic principle of electromagnetic induction, where there will be the more number of turns, there will be more voltage induced. So here you can see that large voltage winding is this. That's why this winding will be called as the high voltage winding, and where the number of turns will be less, that winding will be called as low voltage winding. High voltage and low voltage windings are fixed names. We cannot change until unless we change the number of turns. And other names are there also, primary and secondary. The coil to which we will give the power or provide the power or feed the power is called primary, and from where we will take the power or we will collect the power, that is called secondary. So according to the Faraday's electromagnetic principle, due to the current flow in the primary winding, the flux will be produced, and that flux will be also time varying flux, alternating flux, because current is alternating. Generally currents will be found in the form of sinusoidal nature, so that sinusoidal current will develop on sinusoidal flux, time varying flux, and that flux will be linking with the winding put on the other limb. So that is the secondary winding, and this flux linkage will develop induced EMF, and that is denoted by E here, and E equal to minus n d phi dt, and n is the number of turn, phi is the developed flux, the flux developed by the primary current. Now if we put the value of N here in this equation, that is the RMS value of the induced EMF, we can get the formula that N1 by N2 equal to V1 by V2 equal to I2 by I1. So that equation may be familiar to you because little bit transformer principle is also taught in the 10+2. So now whenever we will come across the losses of the transformer, we will find two types of loss. One is iron loss, other one is copper loss. So two types of metals are there in the transformer. So one is iron, which is the conduction path for flux, and other metal is the copper, that is the conduction path for electrical current. Now whenever we will see that the core is concerned for the transformer, there will be two types of core loss or iron loss. One is eddy current loss, another one is hysteresis loss. Eddy current loss is found due to the alternating flux passing through the material. If the flux is passing through this axis along this, there will be the current lines or current conduction paths depending on the area available here. So we will see the circulating current, and if the area is big, then the resistance will be less and current will be more. So for reducing the area, we can slice it or we can laminate it. That means we can make the solid structure with different type of thin strips or laminates insulated from each other. So one black line here you can see, each black lines are nothing but the thin layer of varnish or one kind of insulating liquid, and after drying it, it will be working as a nice insulator. So each iron parts will be able to conduct the flux, but they will not be able to conduct the current from one layer to another layer. So all currents will be confined in a particular layer only, and that area will be very less. And if area is less, then resistance will be very high, and due to the high resistance, current will be minimized. And if the eddy current is minimized, eddy current loss will be minimized. Like that, you can see the similar type of phenomena in this cartoon, that currents are minimized here by slicing them. So we can find that laminated core in the transformer for reducing the eddy current loss, and then we will get some magnetizing effect. And if we see that magnetizing force, that is H, so that so H will be related to the flux density that is represented by B, and this is the H, that is the per length, the magnetomotive force, that Ni is the magnetomotive force, and magnetomotive force per length is the magnetizing force. So this is the H, and that H is plotted, and the B is plotted over the H. That is, if we increase the current, then we can see that lot of flux, but sometimes after sometimes there will be a saturation point, and due to the saturation point, we will be increasing the current, but the flux will not be increased. So if the flux is not increased, then automatically flux density will not be also increased. And if we want to reduce the current, then we will see that the returning path of this curve is not following the first curve or initial curve. This phenomenon is called the hysteresis, and that can be explained by the granular theory of the magnet, which is already explained in 10+2. So I will just tell that whenever the current will be giving some magnetomotive force, some small granules will be aligned in a particular direction, but whenever we will interchange the current direction, or you will change or reverse the current direction, those materials will not be able to come back as quickly as current can. So that's why there will be some lagging. So that's why there will be some retentivity of magnetic field. So if we make the current zero, also we will see that the material will be retaining its certain amount of flux. So there will be some flux density. And if we want to make the flux neutralized or zero, again we have to put the current or send the current in the reverse direction. So H should be minus in this direction. So this phenomena is called the hysteresis, and depending on the hysteresis loop area, there will be some energy loss, and that energy loss is known as hysteresis loss. So in the transformer, as per the discussion till now, we can see that there are two types of losses which are performed inside the iron core, and that's what is called core loss. And as the core is generally made up of iron, so it is called also iron loss. So if the area is made up of very good material, that's CRGO material or silicon steel, the area will be less, and that's why the hysteresis loss will be reduced. So these are the few constants. We can go through that as a reference. Now we will discuss about the open circuit test and short circuit test. This was about the transformer and its associated losses. So there are two types of losses. One is iron loss and one is copper loss. Iron loss is performed inside the iron. That's why it is known as iron loss. And copper loss is performed inside the copper wires. That is, there are two sets of copper. One set of copper wire, set means say consisting two windings. So first winding is called primary winding, other winding is called secondary winding. So primary and secondary winding both are carrying currents. In the situation where both the windings are carrying current, there will be primary copper loss and secondary copper loss. And this copper loss is nothing but the ohmic loss, that is I square R loss, that is the heat generated inside the resistance of the conductor. Now, whenever we will think about the transformer, so transformers would have some particular amount of efficiency. That means losses must be minimized. Otherwise, if loss is more, then transformer will not be sold or nobody will purchase that transformer. So that's why we need to test the efficiency of the machine before purchasing it. So if the efficiency is good, transformer will be called as the transformer with good performance. But how to conduct the test or how to measure the efficiency? For measuring the efficiency, definitely we need to divide the output by input, and for getting the output, definitely either we need to know the output power, whatever is delivered at full load condition, or we need to measure the losses in some test. So the measuring the losses in the open circuit test and short circuit test is one type of indirect procedure by which we can calculate the efficiency of the transformer. Otherwise, we can simply run the transformer with its full load, and we can deliver the power, we can collect the power at the loads like lamps and fans and all other appliances can be connected to get the full load current of the transformer, and that will be a huge amount of power loss. So for manufacturing transformers in company, it's also will be increased, the economy will not be there, so price will be increased due to the power loss also. So that's why the company which are measuring the transformer efficiencies or detecting that identifying the transformer efficiency, that is generally done by short circuit test and open circuit test, which is nothing but the indirect type of test. By conducting this open circuit test, we can estimate the iron loss, and conducting the short circuit test, we can estimate the copper loss. So how to do that? So what is open circuit? Whenever circuit will be open in a particular points, so there will be no current flow, and that is called open circuit. But when the two terminals of the source or two terminals of the load are getting close together with a zero resistance, that is called short circuit. So there will be no power delivered to the load, and there will be huge current flowing through the source. So this is called the short circuit. Now, whenever one transformer will be there, if any winding is kept open, that is secondary if kept open, but if primary is given or is connected to a power, then it's called open circuit condition. And whenever the secondary is shorted with a wire or by ammeter, then it's called short circuit condition. So this is the panel board, and we will see that there will be transformer, several components will be there, which are the measuring instrument, and those instruments will be utilized for conducting the test. So we will see in the video also. This is the back side of the panel board, and these are the variac or thermostat. This is another view of transformer. Transformer nameplate will be there. What is the power of the transformer? It is generally, we say, named with several parameters. So company name will be there, transformer type will be there, whether it is single phase or three phase. If it is three phase, what type of winding is connected, either delta or star. So many things will be there, at what frequency it is there, for what voltage, what current, primary voltage, what is the primary voltage, what is the secondary voltage. So HV side, LV side, everything will be mentioned in the transformer nameplate. It is kind of the nameplate or identity card. So if we take one example of 1 kVA 55/230 volt 50 Hz 15 in a single phase transformer, then what will be the rated power, what will be the rated voltage, primary voltage, secondary voltage, we will calculate here. So first of all, we have to see that this will be mentioned in the transformer nameplate. 1 kVA means 1000 VA, 1000 volt ampere. And then if the primary voltage is written by 55, why it is called 55 as primary? Because it is written at the left side. So left side voltage will be 55, left side of the slash, and right side will be the secondary voltage. So this will be the primary and this will be secondary. That means if we give 55 volt at the primary, we will get 230 volt at the secondary. We can reverse also. If we give 230 volt at the this winding, we will get 55 at the other winding. So that time 230 volt will be called as primary winding, because power was given in this winding. So now if 55 is taken as the primary winding, so primary rated voltage is 55 volt as it is written here. So say rated secondary voltage will be 230 volt, rated primary current will be 1000, that is this VA divided by voltage. So this is VN into ampere, So divided by volt means it will be ampere. So 18.18. That means primary current will be 18.18. Secondary current will be 4.35 at the full load condition. And rated frequency will be 50 Hertz. Now you have to remember that if we are telling that rated voltage, that means either this voltage and that voltage, primary and secondary will be mentioned. Rated current means 18.18 or 4.35 depending on the winding name, that is primary or secondary. You have to decide that which one is the rated current. So whenever we will tell that 5% of the rated voltage, 10% of the rated current, that means we need to think about which winding we are working with. Only on that winding we will calculate. Also we need to know the full load. Then only on the full load only we will calculate either 10%, 5%, 1% like that. So we have to have this type of clear idea before going to the transformer test. These are the ammeter, these are the voltmeters, and this is the wattmeter. So wattmeter is connected for measuring the power, and there will be two coils, current coil and pressure coils. Now I think you are familiar with the connection of the wattmeter. So if it is not clear to you, we will explain afterward. So this is rheostat, that is nothing but the variable resistance. If we move that spindle, then we can increase the number of turns and increase the amount of resistance included in a circuit. If we move at the leftward side, the resistance will be decreased. So this is the variac internal connection. It is an instrument which is used for varying the voltage. So if we give 220 volt here, we can generate one voltage here. We can get voltage here 0 to 230 or 220 volt. So now we will go to the test. So what is the open circuit test and why to do that? Open circuit, short circuit test are performed on transformer to determine the losses and efficiencies, equivalent circuit and voltage regulation. So now whenever we will do for the open circuit test, generally high voltage winding is kept open. So primary is taken as the low voltage winding. So low voltage winding is taken as the primary winding. We will give the power, and high voltage side is kept open. So here you can see that HV and LV, though the number of turns are drawn with similar winding numbers, but still we will consider this is the high voltage winding. Now what will happen if we give some power here? There may be some more or less power, so that's why we will control that with the help of auto transformer. So we will start from 0 and we will increase the voltage till the rated voltage of that winding. As this is low voltage winding, so as the transformer is taken 55 by 230, so definitely we will go up to 55 volt only. And we will connect ammeter in the series, voltmeter in the parallel, and there will be the wattmeter. So after that we will see that 55 volt will be appearing across this, so voltmeter reading will be there, and automatically there will be 230 volt at the open circuit terminal. So for that measurement we will connect one voltmeter and we will measure the voltage across the open circuit winding, and this is the high voltage winding. So please remember, high voltage side is generally kept open for open circuit test. So we will start the video very soon, and we will go for the short circuit test now, and everything is explained already in the videos, so we can explain the calculation, everything there. So this is the connection. So transformer, low voltage side, that is 55 volt side, high voltage side, voltmeter is connected. This voltmeter is showing the primary voltage, and this will be the primary input current, that is no load current. So these are the all approximation of equivalent circuit. Without reading the transformer, it will be very difficult for understanding the equivalent circuit. But we will just tell you that the approximate equivalent circuit of the open circuit test will be this. And these two currents, that is a core loss component IC and IM, those two currents will be responsible for the flux generation and the core loss. In the open circuit test, the transformer input current, that is called no load current, is denoted by I0. So I0 is entering the transformer, is divided by IM and IC. So we can get these two currents as IC and IM, and resultant will be I0. So this phasor diagram will be obtained, and we can see that the voltage whatever is applied, that voltage is appearing across this and this. So we can get the wattmeter reading, voltmeter reading, and ammeter reading here. Ammeter reading, wattmeter reading, voltmeter reading. So I0, W0 and V0, and we can put those things in the equation. So W0, that is input power equal to V0 I0 cos phi 0. Cos phi 0 is the no load power factor, and cos phi 0 will be calculated by wattmeter reading divided by voltmeter reading and ammeter reading. So now if cos phi 0 is obtained, so I0 is also known, cos phi 0 is known, so IC can be calculated. If cos phi 0 is known, sin phi 0 will be calculated, and I0 is known, so IM will be calculated. If IM is known and if IC is known, definitely R0 equal to V0 divided by IC and X0 equal to V0 by IM. So in this way, we can calculate the equivalent circuit parameter X0 and R0. Those actually we have to calculate in the report. So now for the short circuit test, what is done? Low voltage is short circuited and high voltage is taken for the primary winding. So primary winding means power will be applied to the high voltage winding, and low voltage is sorted with one ammeter. And we will gradually increase the voltage here so that we will get the full load current across this, or full load current through the secondary winding. Now secondary winding is the low voltage side. Low voltage side means 55 volt. So 55 volt winding side, what was the rated current? If we can remember, it was 18.18. So definitely we will increase the voltage up to a certain level, for which we will get ammeter reading of this secondary winding or low voltage winding as 18.18 ampere. So we will see that at a very low voltage only here, we will get current flowing at a full rated condition. So this is the circuit diagram. So low voltage winding will be sorted. Here it is written low voltage side and high voltage side is the primary winding. So the circuit connection will be like this. So transformer is taken. This is low voltage side or 55 volt side. It can be sorted by ammeter because ammeter has very less resistance. After that, variac will be there. Ammeter connection, voltmeter connection, and wattmeter connection. Now we will gradually increase the voltage, and we will see that at very less voltage, means 10 to 15% of the rated voltage. 10 to 15% of the rated means 10 to 15% of the 230 volt. That voltage will be able to send 1.18.18 means 18.18 ampere. So that voltage will be sufficient to send the current, this much of current. So we will play the video now, and here also we will get the similar equations. If you go through the manual also, you will find the same equation, because here we can see that WSC is equal to R equivalent, that is the equivalent resistance of the transformer at the short circuit condition, and that is nothing but one resistor and one inductor in series. So if we give the voltage VSC and if we measure the power WSC and if we measure the current ISC, then you can get the power is nothing but R equivalent into short circuit current square, and from there R equivalent will be obtained, and Z equivalent will be obtained as Z equivalent means Z means this one, R equivalent and J X equivalent. So this will be Z equivalent, and that is this entire drop is coming here. So Z equivalent will be VSC divided by ISC. Now if Z equivalent and R equivalent is known, if Z equivalent and R equivalent known, then automatically we can get the X equivalent, because Z equivalent equal to R equivalent plus J X equivalent. And here we can see that output power divided by output power plus iron loss plus copper loss. So here we can see that the short circuit power WS is nothing but the full load primary loss, primary copper loss plus full load secondary copper loss. So those two losses will be entire copper loss of the transformer at full load, and that will be obtained from the wattmeter reading. So iron loss is obtained from the open circuit test, copper loss is obtained from the short circuit test, and output power, you know what is the kVA output rating. So we will multiply by 10 to the power 3, and to power factor we can consider one power factor as 1, as well as we can take any other value 0.9, 0.95 like that, and you can multiply with 100 to get it in percentage. So this is about your experimentation. So this is all the chart which are already mentioned in the manual. So instrument or apparatus here, and we will provide the results and you can calculate the equivalent circuit parameters for open circuit test and short circuit test. So that's all from my side. If you have any doubt, you please ask so that we can explain, or otherwise we can ask at the end of the experiment video also.
Yes, sir. You stop. I think.
Yeah. So yes.
Yes. Is it visible?
Yes, sir.
Yes, sir. Yes, sir.
But listen carefully. I have increased volume also 100%. Is it audible?
No, sir.
No, sir.
No, sir.
No, sir.
No, sir, it is not audible.
Just wait. I'm sharing again. Yes, it is visible now. And now I think it is audible also. You see and listen.
This is our electrical technology laboratory.
Is it fine? It is audible?
Yes,
Yes,
sir.
sir.
Audible. Yes, sir.
List of experiment. Okay, here you can see experimental table that you can check this network theorem 1. Another setup for this network theorem 2. Another setup for this. Again, this is fluorescent lamp. Same setup for this. And here calibration of energy meter. This experimental table for 3-phase star delta connected load. Here, this one is for single phase transformer experiment, open circuit short circuit test. This table is here, another table. Same that for open circuit and short circuit test verification. Here, the calculation of different kind of incandescent lamp. Here you can see this one. This is the experimental table for that. Here, this is another setup for that. Different incandescent lamp are connected here. This is a study of series and parallel circuit. In parallel RLC circuit it is. So this is experimental for that. Another one. This is another setup for same experiment. Study of series and parallel RLC circuit. So this is overview. Okay, thank you. Today we are performing.
Now it is properly audible and visible also.
Open circuit and short circuit test on single phase transformer. So here we have to see this is a single phase transformer. This
now
is
it is properly audible
primary.
and visible also. Yes.
Yes, sir. Yes, sir.
And secondary. Yes, okay. So this is primary and secondary. So primary and secondary we can change as per our requirement of the system. We are performing open circuit or short circuit test. Okay. So this is basically the single phase transformer actually. Okay. From here you can check, and this side is 54 volt side. This one here. Okay. This is basically 220 volt side. This connections one this side 220 volt side. Okay. So first we have to see the connection diagram of open circuit test. You check this one. So here apparatus required are one single phase variac, one emitter, 2 voltmeters, 1 wattmeter, and wattmeter should be low power factor wattmeter. Okay. So because this is no load and open circuit test in the secondary, we will not connect any load at that. So very a low power factor is observed here. So LPF power factor wattmeter we will use here. Okay, and we will perform here. You see the open circuit test on which side? The 220 volt. It means open circuit voltage always perform on the high voltage side. So here high voltage side is 220 volt. Low voltage side we have to connect all the meters, measurement meters. This is basically 54 volt side. And your input voltage is what rated value of input voltage here. If we perform the open circuit test here, so input voltage, rated voltage will be 55 volt. Then you will not supply more than the 55 volt. Okay. So you have to observe. You have already seen this connection diagram. Okay. So here, according to the connection diagram, we have to connect the circuit here. The range of the different meters here you can check. This supply is 220 volt or 230 volt. Okay, this emitter, this is 0 to 1 ampere. Lpf voltmeter we have. Okay, this is Lpf voltmeter. Okay, specification we have already we will already see. That we will see later. Okay, now this voltmeter whatever will connect on the primary or that 55 volt side, this is 0 to 150 volt, and secondary side this is basically 0 to 300 volt, because the rated voltage is secondary side is 220 volt. Okay, that's right. Okay, according to this connection diagram we will connect. Okay, we will start the connections. So this is basically supply. Here we have connected this is single phase variac. Here you can see this single phase variac, this 2 terminal of single phase variac, it is here. So after that single phase variac you have seen in the connection diagram, the emitter is here. Okay, so after the single phase variac, here you can see parallelly single phase variac, after the emitter, and it should be 0 to 1 ampere range. After that M terminal of the voltmeter, after M to C short. Okay, M to C short. After that M in means it as C for common, that L it means after that load will connect. Okay, so L terminal, L to the primary winding or 55 volt side you have to connect. Okay, after that V basically again we connected to the negative of the single phase variac here. Okay, and again the same terminal will go to the another terminal of the primary winding 50 volt side. Okay.
Hello, video has stopped. Hello, sir.
Hello.
Yes, sir.
Yeah, there may be some
Yes.
internet issue from Ashish sir. Okay.
Okay, sir.
Okay, please wait.
Sir?
Yeah, tell me.
Sir, the Viva portion is from which portion? Is it a theory portion or from practical portion?
Yeah, your lab viva will be from your laboratory experiments only. Okay, related questions will be asked. Related.
Okay.
Sir, when will be our Viva happen?
Hello, Tushar.
Yes, sir.
You got my answer?
Yes, sir. I got it.
Okay.
Sir?
Yeah, Subham, tell me.
Yes, sir. When will the Viva happen?
Before your examination starts, so we will inform by today only. Okay.
Okay.
We need to discuss between us. After that, date will be fixed and it will be informed to you.
Sir, please give us 1 week time.
Yes, yes.
Yes,
it will
sir.
be given.
And sir, what is the deadline of the submission of the practicals?
Yeah, that will be generally say by this weekend, coming weekend. Okay. Generally means not sure, but we will discuss and let you know by today night only. We will send the information through
Yes, sir,
email and WhatsApp groups.
Sir, give us at least 8 to 9 days for writing down all the 8 experiments.
Okay, let's see. Okay.
Okay, sir. Thanks.
Okay. Hello.
Yes, sir.
Yeah, I think Dr. Bohre is out of the network, so
Yes,
I will
sir.
play the video for you and
Yes, sir.
I will share. Okay.
Okay, sir.
Okay. So can you hear the voice?
No, sir.
No, sir.
No. Okay, let me check. Now?
No, sir. Still, it is
No,
not
sir.
audible.
Now?
No, sir.
Sir, I think on presenting audio is not permitted. Yes, sir. No comment.
Now you can hear?
Yes, sir.
Yes, sir. Now it
Okay.
is okay, sir.
Okay. So till what point you missed that? Means till what point it was fine?
558.
So
Yes, sir. Okay.
This is okay, na? Okay.
Sir, audio is not coming, sir.
Audio is not coming, sir.
Audio is not coming?
Yes.
No, sir.
One minute. Now you can hear?
No, sir.
Sir, play the video.
You can hear?
No, sir.
No, sir.
Oh.
Sir, you have to share a window, not the screen, sir. You have to reshare by a window.
Okay.
And there's an option called include system audio.
Now it's audible?
Sir, video has not started yet.
Okay. But you can see, you can hear anything?
Sir, I think you are not presenting.
But it's showing from my side, it's presenting. Hello, anybody can see the video?
No, sir.
No, sir.
No,
No,
sir.
sir.
So probably
sir.
rejoin once. Try rejoining. रोहित भाई रूबीज की सॉल्व हो गया?
भाई भाई एक हफ्ता टाइम मिल गया तो बढ़िया, नहीं तो लो चलो
10 दिन करा भाई, एक
हाँ
सप्ताह
हाँ
का
वो
होगा
हो जाएगा।
अटेंडेंस।
हाँ भाई वो तो इंटरेस्ट है। अरे पहले तू सर से कुछ
सर
पूछ
आ गया,
रहा
सर आ गया।
Yes, I am audible or not? That what happened? It's till that
Sir,
which
now
point we have. Hello. Maybe that internet issue just cut off that thing. Okay, just wait. I will share up to which point you have seen. I will play again. Just wait.
there is an option click on it.
What happened?
Actually, I am saying while sharing your screen, the system audio.
It is okay. Fine. Now at the which point I am asking which point you have seen.
8.58.
8.58. After 8.58,
So
you are not able.
558.
558.
Oh, 550. After that, you are not able to see.
Audio was not available, sir.
Oh, just wait. I think. Just wait. I have to see again. Just wait 1 minute.
M terminal. Here you can check.
Is it fine? It is coming.
Now,
audio is coming.
Yes, sir.
M2C should be
Now
shorted.
check.
Here we have used this.
Okay, so from here, approx 6 minutes. Huh?
Yes, sir.
This is common. After that, this is 1 ampere. 1 ampere range we have connected here. You can see this one. This is the 1 ampere. This is 2 ampere. This is 1 ampere. We have connected at 1 ampere. Okay. After the 1 ampere, this terminal goes to where it will go. You see at voltmeter to measure the input power. This measuring this input current. This will voltmeter will measure the input.
Is
power.
it audible and visible also?
So here at M terminal.
Yes, sir. Audible and visual.
M. Now M2C should be shorted. Here we have used this wire to short the M2C. After that, from L terminal, this is L. We have connected this is L. This is 55 or LV side binding. Okay, 55 volt side binding. Okay, we have connected. And the negative terminal, this is positive one. Then negative terminal of this low voltage side is again connected to the negative of the single phase barrier. Here you can see this.
Yes,
Okay.
it is audible.
Now, one more connections for the voltage of
Yes,
VV
sir.
terminal of the wattmeter. Here you can check this one. The V is connected to the negative of the voltage as you have seen in the connection diagram. It is connected here, as you can see this way. Okay. So this primary connection you have done properly. One more connection to measure the voltage across the primary side voltage. Okay.
If it is not audible, you
We
just
have to
immediate me.
connect
Okay,
one
just immediate
voltmeter.
tell me,
This is
sir,
the
it is not audible.
voltmeter
Okay.
range will be, because we are measuring the primary side 55 volt. So voltmeter range here not 155 is available. So minimum range available is 150. In 150 we will connect. You see this two terminal. We have connected this basically this side here 55 volt, another one at we have to see, just we will connect at 55 volt side this one, and another one that to measure the open circuit volt at high voltage side. So I am connecting. Okay, this one terminal I have connected here. Okay, this one, and 150. This is basically 150 volt side. This is 150 volt side. I am connecting here in the negative terminal of 55 volt. Here I have connected. This connection was not connected earlier, that's why I am doing here only. Okay, this is basically measuring the input voltage on the primary or the low voltage side, and this is already connected. As you can see, this is connected to high voltage side, 2 to 20 volt side, to measure the open circuit voltage. Here it is connected, and this is again at which range we have connect. So we have to connect this 0 to 300, it means common, and this is 300. So basically the common is connected to the positive. This you can see common is connected to the positive. Here it is connected.
It's fine now.
And negative to that you can check.
Yes,
Okay.
sir.
To the this wire gone here to 300. This will give you the open circuit voltage on secondary side. Now very important thing here for voltmeter. Okay, so voltmeter here you are seeing the okay different voltage, but here the concept of multiplying factor is there. So we have to see the nameplate specifications. Here you see this is basically nameplate for voltmeter, and here what connection we have made, we have to see here. If the V1 V2 is connected, here you see one strip is connected between the V1 and V2, it means the connection, internal connection is V1 V2. So this will decide the current rating. Okay, if E1 E2 is connected, then other range is there. If V1 V2 is connected, then other range is there. Okay, and voltage also you see that two voltage there, that's 250 and 125. Okay. So based on that, we have to decide the multiplying factor. So we have to see the nameplate. You see here it is written multiplying factor. I think it is more clear now. The current we are operating, it means B1 B2. From where we will get that connection? Here you see B1 B2 is connected. Just I shown you. This B1 B2 is connected here through the strip. So B1 B2 is connected, then current range is how much? 1 ampere. And we have connected at which terminal? 125. So you see 125 for multiplying factor here. If 125 it is there and 1 ampere is there, multiplying factor is how much? 1. So whatever it will measure, that will be your true reading. Okay, if multiplying factor is 2, so to find the actual reading, basically whatever voltmeter gave, we have to multiply by its multiplying factor. If you are operating 2 ampere, okay, you connected E to B1, B to E1 like that, then in case what will happen, you are operating at 125 and 2. So here basically your multiplying factor will be 2. Then whatever voltmeter reading will come with 2, then you have to always multiply by 2 or whatever the multiplying factor. Okay, so this is basically. So here is a very easy one. So here multiplying factor is 1. So not need to multiply anything. Always whatever reading will come, you have to take that. So we have to take now reading. We will note down the reading.
Till now everything fine now? It is audible as well as visible properly.
Okay.
Yes, sir.
And this basically this is your observation table for open circuit test. As you can see, this OC test. Okay. For this, now come, we will switch on the supply. Before that, we have to ensure that our variax should be at 0 position. As you can see, it is this node at 0 position. Okay. Now we can switch on the supply from here. We'll switch on the supply. Here, light is glow. Light glow, it means supply cam. Yeah. Okay. Now we will start. This open circuit test is performed on the rated voltage. We will give rated voltage how much? 55. Okay, because primary is 55 now. High voltage, low voltage primary and high voltage secondary. So from here, now all of you see here what's the meter it will give. This is our primary meters. We have to see this one. We should not more than. Now we are increasing from here. See this simultaneously we are increasing slowly, slowly, slowly. Now check the voltage also here. Check the voltage. We have connected at 150 side. It means here you see the two reading is there. Two indication of this 155. So 150 is it is lower side. Okay, if it is connected at 300, then you have to see upper scale. Now lower scale you have to see here 150 range at lower side. Okay, so now it is increasing. I am just increasing.
Why do you disconnect?
Now you see this indication is increasing. Okay,
or internet issue.
Now it is 50. It is reached to 50. Okay, we have to go 55. It means I have to increase little bit. 5 value. Now it is 55. You see, this is primary voltage. It is 55 now. Okay. Now see the secondary voltage here. Secondary voltage, open circuit voltage. How much? This is approximately 220. Approximately, not exactly, or more than that. But 220 is like that. Okay. Whatever voltage will come, you have to take only one reading. What is the primary current here? You see here this primary current. This is the primary current value. What is the voltage? Input voltage. What is the input power? You see from here to here. You see this one. It is basically now 16. This is 18. Between that, this is 17. Approximately, it means 0 to 1 ampere. 0 to 1 ampere range. So we will see the lower scale value. Okay. So 0 to 1 ampere is lower scale one. So we have to take. We have to see this is basically 230 volt. More than that, approximately 230 volt. We have to note here 230 volt. Okay. No load current. We have to check here. We have already noted down no load voltage. This is wattage also we have noted down. Okay. Here wattage also we have noted down. Approximately 17 it is there. Okay. So input voltage we have noted down. And the second, it means primary voltage, low voltage side voltage, and high voltage side voltage we have noted down all the things. Okay. So after that we have to calculate the parameters. Okay. Open circuit test parameter. So open circuit test parameter based on these formulas we have to calculate. Okay. First we have to calculate the power factor, no load power factor. So cos phi naught equal to W naught upon V1 into I naught. This parameter we have. Okay. This is separate formula. From here, IW, it means working component. Is it
visible and audible properly? Yes.
Yes, sir.
Okay.
This IW equal to I naught cos phi naught. Magnetizing component, it is basically I naught into sin phi naught. Just put the value, you will get this value. After that, you have it is already discussed in the theory that if it is not discussed, later on it will be discussed. So for the open circuit test, what is basically your equivalent circuit diagram is this. It means IW here, this is IM here, this is because in the secondary side you will not connect anything. So final equivalent circuit for the open circuit is this one here. V1 is supply voltage is there. So this is approximate equivalent circuit for the open circuit test. Okay, this is basically I. This is I1. I1 have, or the, we can say I naught. No load current is here. Okay, so that's about the open circuit test. After finding this, we have to also calculate the R naught value and X naught value by putting this value. Now you have all known quantities.
So this is all about the open circuit test. Okay, I'm audible. This is all about open circuit test, and here that we have seen while calculations that their zero error is not removed in the meters. That's why that reading is not proper. So we have shared in that MS team the correct reading after verifying it. Okay. So during in hurry we have recorded these videos. It's fine. when lab is started. So that's fine. That you take correct reading in that we have shared the exact reading for open and short circuit test. So you do the all calculation through that only. Okay. So now I'm playing a video for the short circuit test also. Okay. Is it okay?
Yes,
Is
sir.
it visible?
Good evening all. So we are again in the laboratory of electrical technology.
It is audible?
Yes, sir.
Yes, sir. Yes, sir.
And today we will discuss about the short circuit test on the single phase transformer. So here you can see the panel board, and that panel board is suitable for understanding the connections. And near the panel board, the experimental table is there. We can see all the experimental components or instruments are connected already. We will be discussing that, how it has been connected. And lab manual is there, so you will go through the lab manual and circuit diagram. So now we will do the short circuit test of the transformer. So we will follow the short circuit test circuit diagram. As the circuit diagram shows, we need to connect the transformer as shown in this figure, and all the components are shown here. So what type of instruments are required? First of all, we will see the transformer. Same transformer will be used, what has been used during our open circuit test discussed earlier. And the rating of the transformer is 1 kVA transformer, power rating, and 220 volt / 55 volt. So here we also see from the panel that 220 volt is the high voltage side and 55 volt is the low voltage side. Now, as a thumb rule, we will short the low voltage side. That means we will apply the power to the high voltage side, that is 220 volt side. So that power will be consumed as the full load copper loss of the transformer in this short circuit test. So short circuit test, as it has been already explained in the theoretical discussion classes, that is conducted to estimate the full load copper loss. So there are two windings, so there will be two losses, primary copper loss and secondary copper loss, and the wattmeter which will be used in this experiment will give the reading of the total copper loss, that is primary copper loss plus secondary copper loss. Here primary winding will be high voltage side winding. We will choose that winding as the primary winding because we are going to give the power from the variac or thermostat. We will be giving the power, and that's why this winding 220 volt side winding will be called as the primary winding and 55 volt winding will be called as secondary winding. So as per the short circuit test, secondary winding will be sorted directly by any wire, or we will be sorting with an ammeter, because ammeter has also very less resistance. So if we connect ammeter as shown in this figure, so we will consider that winding has been sorted. Okay, so now we will be discussing about the component or instrument. First of all, the 220 volt variac will be there. So we will get maximum 220 volt, or even we can go for the more depending on the manufacturer specifications. After that, we will use one ammeter to read the input current which will be consumed by the primary winding, that is 220 volt side winding. And after that, the wattmeter will be connected. Here you can see that M, L, CV points, which are very well known to all this time after discussing several times during the theoretical classes. So M and L will be the current coil, and MCV that will be showing the pressure coil or voltage coil. So M stands for say main, and L stands for line, C for common, and V for voltage. And after that, we will see that there is one voltmeter which is connected in parallel, as the voltmeters are connected always in parallel. So that voltmeter will be measuring the primary voltage or input voltage, that how much voltage we are giving. So we will be changing the voltage in the variac side. We will be reading that voltage continuously at the voltmeter, that is shown here. 0 to 50 volt range is a very suitable one, but any voltmeter is possible to be connected. But here we will see that the voltage required for this experimentation will be 5 to 15% of the full load voltage, that is 5 to 15% of the 220 volt side, means 220 voltage is the rated voltage. So 5 to 15% of the 220 volt will be the required voltage, minimum required voltage to send the full load current through the secondary, that is in the 55 volt side. So how to get the reading of the secondary voltage, secondary winding? Because we have already connected the ammeter, so we will get the ammeter reading and we will get the current. And as for the transformer specification, that short circuit current can be calculated from the kVA rating. So kVA rating is 1 kilovolt ampere. So definitely 1 kilovolt ampere should be divided by 55 because that side, secondary side, is the 55 voltage side. So automatically we will get 18.18 or 18.2 ampere. So that type of ampere current is called as the full load secondary current. Now we will be discussing about the real experimental setup, that how all the instruments are connected. So first of all, we will start from the main supply board, which is installed on the wall of our laboratory. There will be one 3-pin plug and switch, which will control the main supply. That is switching on and off, will give some power and disconnect the power. After that, thermostat will be there, and thermostat will be rated with the scale. But due to several usage or due to some manufacturing, say, mismatch with the rotating knob and the scale, we cannot tell that exactly whatever is shown on the scale will be going to the input side. So that's why we will be using some voltmeter. Here we will be using the panel meter, digital voltmeter or digital panel meter, which is shown here. So here you can see these two wires are coming, and these two wires are connected across this 220 volt side winding. So it will be measuring the voltage coming from this thermostat. So we will get an idea from this scale, but exact value will be displayed by this panel meter. Okay, after that we will get the emitter connection. So we will start from the positive terminal of the variac, that is this one is considered, though we can consider this also, but here we have considered this one as positive. So we will keep in mind, and red wire is going to the input of the emitter, and that input of the emitter will be connected to the common point, and after that the emitter will be connected to the 5 ampere range, because the full load primary current, so we have connected the 5 ampere range, full load primary current will be 4.5 approximately. So it will be also calculated by dividing 1000, that is 1 kVA divided by 220, because we are going to measure the current through this primary winding, which is high voltage winding, so 220 volt side winding, and total power is 1 kVA divided by, so it will be 4.8 will be suitable range. So we can see that 4.8 range is there. So let's see how much current is coming, because if we connect to a 2 ampere or 1 ampere range ammeter, then it will not be suitable for reading that, because the expected value or measurand will be little higher than that. So it is better to connect with any ammeter greater than 5 or at least 5. So we have connected to a 5 ampere, 0 to 5 ampere ammeter. Okay, so after that ammeter connection, the ammeter is going to the point M, we can see. So we will also see that the ammeter wire is coming, and this wire I will show you clearly. So this is the ammeter. So this is the ammeter wire is coming, and it is going to the point M. So this is the point M.
It is properly audible and visible.
And after that M is the current coil starting point. So ending point is the L, and that L
is properly audible and visible.
Going to the
Yes,
going
sir.
to the L will be going to
Yes, sir.
the primary winding or 220 volt side winding, and that end point will be going back to the voltmeter point. So that it is displayed here in the circuit diagram. And now point to be noted that M and C points are not connected directly. M and C points are not connected directly for the wattmeter, so we need to sort it out. So that's why we have connected the C means common point of the wattmeter. C is connected by one wire. So this wire is taken as a longer. We can use the short wire also. That is also possible. So M and C are sorted. And after that, the wattmeter negative point or the voltage terminal, which is connected here with This is the 150 range. We can see if we make it straight. So I think the 150 is not clearly visible to the wire connections. Now it is visible, I think. Or yes, it is 150 volt connection is there. So green wire is connected to 150, and that 150 voltage or volt point is going to the returning path of the variac. So in this way, the circuit diagram is completed. And in the secondary side, that is in the low voltage side, that is 50 volt side, 55 volt side, we will connect one ammeter as we have told. So one point from the positive terminal of the 55 volt is coming to the 30 ampere range, and the negative point of that point of the secondary coil is coming to the common point. So we can see here in the common point it's connected. So secondary side is also connected by one ammeter, and that ammeter is used to measure the secondary short circuit current as well as to make the secondary shorted, because ammeter has very less resistance, so definitely it will work as a short circuiting element, and that current will be 18.18 or 18.2 approximately current ampere will be flowing at the condition when the 5 to 15% voltage of the primary is applied. Why that 5 to 15% voltage is sufficient to send the full load current through here? Because whenever there will be lamps, there will be loads. But in the short circuit conditions, the lamps will not be there, no load will be connected, so only one small wire will be there, which is very less resistance. So very less amount of induced voltage here will be sufficient to send at least full load current 18.18. Now for inducing that small amount of voltage, primary voltage also will be required very small, not the full is required. So that's why 5 to 15% of the 220 volt, that is of that winding rated value, is required to send the full load current through the secondary one. Here you can see that as the current value is high, that is 18.18 ampere, so definitely we will be seeing we have connected to a higher range, that is at the range of 30, means we will be connecting to the 30 ampere range, so that it comes under this measurement value. There are other scale is also there 15, but as the 18 is more than 15, so we will not choose that 15, otherwise we will not be able to measure the full scale deflection. Okay, so now we are going to switch on the powers. So those two plugs are the power to the thermostat as well as power to the panel board, so that we can utilize the digital panel meters, because digital panel meters need some power. Okay, so now we will increase the power or increase the voltage by rotating the knob of the thermostat. We will gradually increase, and we will see how the meters, that is ammeter, voltmeters, are showing. So right now the voltage applied to the input increasing gradually, and you can see that the power is being consumed by the transformer, so power is increasing. And ammeter, the input current to the primary winding also is being measured, that is connected to the 5 ampere range, so upper scale will be considered. And in case of the secondary winding also, we are seeing that high value of current is going. So now it has reached to the 18 ampere, so it is approximately the full load current. And for that full load current, the required primary voltage is 18 volt, so which is the very less value compared to the full rated value of the primary winding, that is 220 volt winding. So 18 is very less, 18 or 17. So it comes under the range whatever is mentioned in the manual. So now we will note down all the powers, amperes and secondary amperes readings, and also we will take the voltmeter reading of the primary winding, so that we can calculate all the circuit parameters as explained in the manual. So here we can see the primary voltage, so we will note down as 17 volt. Primary current, that is ISC or I short circuit, so that will be found from this ammeter, which is connected to the 5 ampere range, so we will take the upper scale. So it is 4.4 and then it is 4.5, 4.45. It is coming approximately 4.5, but we will write 4.45. Okay. And after that, wattmeter reading. Wattmeter reading will be.
Is it audible properly and visible also?
A little bit fluctuating.
Yes, sir.
So,
Yes, sir.
now for wattmeter reading, we need to check the multiplying factor for wattmeter. And for checking the multiplying factor, we need to know at what ampere range and at what voltage range wattmeter has been connected. So here you can see that B1, E2 is sorted and B2, E1 are sorted. These knobs are for controlling the current capacity of the wattmeter. And depending on the connection, which is mentioned in the nameplate of the wattmeter, we can see this connection, that is B1, E2 and B2, E1, when it is when these are sorted, it is for the 2 ampere range. Here we can see that. And also we have already explained or mentioned that wattmeter voltage rating is connected to the 150 range. Here we can see. And for that also we can get the voltage rating. So we will see that for 2 ampere and 150 volt, the multiplying factor is 2. So whatever reading will be obtained here, the value,
it is properly visible.
That wattage is required to be multiplied with 2 so that you can get the actual power consumed by the transformer at the short circuit condition. So
hello, Assis.
Sir, it is stopped now.
Yeah, stop now. I'm contacting with Dr. Assis.
Hello. So, sir.
Hello.
Yes, sir. It is again disconnected due to that network is coming and going. Okay, I am again sharing.
Yeah.
Just now. Yes, that it is creating some problem. Internet. Okay, fine. I am again sharing this thing. So is it fine till now that you have seen? I think just sir told about the parameter. Yes?
Calculate the RSC.
Is it fine for all of you?
Yes, sir.
Yes, sir.
Yes, okay.
And we need to calculate the ZSC and XSC. So RSC, XSC and ZSC all are the equivalent circuit parameter, which has been explained in the discussion classes. And we need to take the values of wattmeter and ammeter and voltmeter so that we can get the values of RSC. As it is shown, the RSC will be calculated by dividing the wattmeter reading by the square of the short circuit current, and ZSC will be obtained by dividing the voltmeter reading, that is VSC, by the short circuit current value, that is ISC. And whenever we will have the ZSC and RSC, we can calculate the XSC, that is the reactance part, equivalent reactance of the transformer at this condition. So it will be root over ZSC square minus RSC square. So root over line will be equal to be more, yes. So it will be a little bit more here, yes. And after that, we need to calculate the efficiency of the transformer whenever the primary copper loss and secondary copper loss is already known, and also the
transformer iron loss is known, so we can get the idea about the entire loss. So in the formula, you can see the efficiency is calculated by the standard formula, that is output by input. So output power is already mentioned here, and the copper loss and iron loss is added to the output power, and we can calculate the efficiency. So from the open circuit test, Wi, that is iron loss, is obtained as the wattmeter reading at that condition, that is open circuit condition, and for copper loss, it is the wattmeter reading in the short circuit condition of the transformer. Thank you.
So this is all about the test. Okay, the video is already shared. Okay, Tushar sir, I'm audible.
Yes, you are audible.
So that if any questions regarding this test, you can ask. Or some discussion you want? Yes, that readings we have already shared. Manual we have already shared. If you want, we can show you regarding the videos and all material is already shared. You can download from here. Okay, so I just show you in this year group only. You go in the file section. All of you have seen that or not?
That class material.
Not class material, lab material.
In the file, it is mentioned that class meeting, and under the class meeting, there is experiment 1 to 8.
You see here all. You see, I'm showing. Tushar sir, is it visible or not?
Yeah, it's visible.
You see all recordings. Okay, that all experiment wise recording, it is there. Okay, that I will show you other file also in this only, that different experiment in this. You see that yes, you see all experiments is there 1, 2, 3, 4, 5. Okay, so you see here this in the file section regarding this. You will see in the sections, you can see this all the you see the practical lab laboratories, that's all recording the schedule, it is uploaded by sir. Okay, so all things, that experiment basics, what is that, the recording also. Okay, so you can see here also the different recordings, whatever we do, different experiment it is available, whatever we have explained. Okay, so that it is already available with you. Okay, so if you have any doubt or anything regarding the calculation of parameters, so just updated. Sir, it is shared now. Updated readings also it is shared. Tushar sir.
Yeah, we shared that, but few students told that there is no result. So I think wrong file was shared.
Oh, okay. So fine. We will check, and by today only we will share.
We will upload by today.
Okay, fine, sir. Thank you. Okay, fine. So any doubt or any discussion you want? Tushar sir.
Yeah, please respond, students. Dear students, if you have any doubts, queries.
Okay.
Okay, fine.
You can also contact anytime through email or WhatsApp regarding your query. Okay, I have made the groups for EES51. So we can post.
Sir.
Tell me.
Yes.
Sir, we have, sir, on a practical we have a group, मतलब 7-8 पार्टिसिपेंट एक में होंगे.
हाँ, एक में होगा.
Schedule, Viva schedule and date and groups, whatever distribution, and that will be inform you shortly. Okay, I think, sir, it is fine that we will inform him and upload all the things.
Yes, we'll do it by Monday only. So
by Monday, yes. Okay. And all of you ready with your files? Very soon we will share the assignment link where you have to upload all the files. Okay, experiment file in the MS Team only. Okay.
Okay, sir.
Thank you. All of you can leave now. Thank you very much.
Thank you, sir.
Okay, thank you, sir.
Thank you, sir.
Thank you, sir.
Thanks all. Yeah. Keep posting me if you have any doubts and if you have any queries. Okay.
Sir, we can post it on WhatsApp now, sir.
Yeah,
On the
yeah.
WhatsApp.
I generally reply as soon as I get the message. Or if you don't get me reply, then you just put the message again or give me a call.
Okay, okay, sir.
Yes, and if any doubt regarding the submission, so you can call directly to Tushar sir or Rajiv sir. Okay, they will respond if some problem you are facing, something like that. So, and we are also here, but if you can not able to call or not that they are not picking, so you can call us also. Okay.
Yeah, yeah. You can call any instructor. Okay, any teacher.
Sir, have you taken attendance?
Yes, it is already taken. That automatically. Don't worry.